Water is the most abundant and affordable fire-extinguishing agent on Earth. As this diagram illustrates, a single gallon of water absorbs over 9,000 BTUs of heat energy as it physically changes from a room temperature liquid into steam. But movies usually get the delivery method completely wrong. Someone holds a lighter to a single sensor or pulls a wall alarm, and instantly, every sprinkler in the entire building goes off at once. In reality, drenching a whole skyscraper just to put out a trash can fire on the third floor would cause millions of dollars in unnecessary water damage. Water is also full of natural liabilities. It expands when it freezes, it conducts electricity, and easily destroys sensitive modern electronics. To balance fire suppression against total property destruction, engineers don't use one universal plumbing layout. They rely on 4 highly specialized delivery systems to ensure the water only goes exactly where it has to. The most common setup is the wet pipe system. In this baseline design, the entire plumbing network is fully pressurized with water, right down to the individual ceiling fixtures. Look closely at the sprinkler head, specifically the small blue glass bulb. That bulb is a heat-sensitive physical plug. When a localized fire raises the temperature directly beneath it, only that specific bulb shatters, releasing water over the immediate area, while the rest of the building stays completely dry. But keeping water waiting at the ceiling is a huge liability in unheated structures, like parking garages. In winter, the standing water will freeze, expand, and shatter the piping network. To protect those cold environments, engineers use a dry pipe system, which swaps the standing water out for pressurized air or nitrogen. That air pressure acts as a physical barrier. It pushes against a specialized valve located further back in the plumbing network, usually hidden safely inside a heated utility room. This cross-section schematic shows how the dry pipe valve reacts. When a fire breaks a sprinkler bulb, the pressurized air escapes. As the internal air pressure drops, the valve flips open, finally allowing the water to rush into the network. This creates a mechanical delay known as water delivery time. Engineers have to carefully calculate the trip time, how long it takes the air to bleed out, plus the transit time for the water to travel the length of the empty pipes to reach the fire. The dry pipe design intentionally sacrifices an instant response to guarantee the pipes won't freeze and burst before a fire even has a chance to start. Some environments pose risks that outpace a localized response. Notice the massive scale and high-value equipment in this aircraft hangar. Highly flammable materials here mean a fire will spread much faster than individual glass bulbs can react. This is where the movie trope is actually real. In a deluge system, all the sprinkler heads in the network are permanently open, with no glass bulbs to block the flow. Because there are no physical plugs at the ceiling, the system relies on a completely separate, highly sensitive electronic detector array. When those sensors detect a hazard, they trigger one massive central valve. Facilities like this accept total water saturation as a necessary trade-off. Overwhelming the entire room with water is the only reliable way to prevent the total loss of the structure. On the opposite end of the risk spectrum are rooms where water is almost as dangerous as fire. If a pipe were to leak inside a sensitive computer mainframe room like this one, the hardware destruction would be catastrophic. To protect these spaces, engineers build a pre-action system. This setup acts as an extreme fail-safe, combining the empty, pressurized pipes of a dry system with the electronic sensors of a deluge system. It requires a strict double-knock verification before a single drop falls. Phase 1 happens when a separate smoke detector senses a fire and tells the main valve to flood the dry pipes with water, but the individual sprinkler heads stay completely closed. Phase 2 requires the heat of the fire to physically shatter the individual glass bulb directly above the flames, which finally clears the path for the water waiting in the pipe. Pre-action systems highlight a harsh reality in modern engineering. Sometimes the hardest part of fire suppression is strictly controlling the cure. Selecting a mechanical delivery system is where the engineering begins. This grid represents the reality of hydraulic calculations. Engineers must mathematically prove the network pushes a precise density of water to the most remote corners. But every turn, narrowing diameter, and elevation change causes friction loss. These choke points drain the water's kinetic energy. We rarely think about this invisible web of math and fluid dynamics when we glance up at the small metal fixture on the ceiling. Fire sprinklers are highly calibrated, context-aware machines. mathematically tailored to defend the exact room you are standing in right now.